A massive solar storm will not melt our digital infrastructure. It won't break a single piece of hardware. A severe space weather event threatens the global grid by destroying the one mathematical constant required for the modern economy to function: time synchronization. Everything from algorithmic stock trades to cellular networks runs on Coordinated Universal Time, or UTC. It is the definitive bedrock of global data exchange. But our devices do not actually know what time it is. UTC is maintained by a highly isolated ensemble of primary atomic clocks kept in controlled laboratories, and it is broadcast to the rest of the world exclusively via L-band radio frequencies, transmitted by satellites in Earth orbit. The terrestrial endpoints of this vast system are highly sensitive ground receivers. They sit in data centers and telecom towers, continuously listening to space, absorbing the timestamps beamed down from above. Modern infrastructure doesn't generate time, it simply receives it. This architecture creates a single, invisible point of failure spanning the entire globe. The threat begins with a coronal mass ejection. When the sun ejects 1 billion tons of charged plasma, that extreme solar radiation inevitably collides with Earth's upper atmosphere. This radiation drastically spikes the total electron content in the ionosphere. What is normally a clear, predictable transmission path for radio signals instantly becomes a turbulent, heavily ionized barrier. As the 1575.42 MHz signal hits the turbulent ionosphere, it experiences severe refraction. These erratic phase fluctuations are ionospheric scintillation. Inside the ground receiver is a phase lock loop. If shifts occur faster than this loop can mathematically track, the receiver drops the signal permanently. If that phase lock loop fails at scale during a Carrington-level event, the entire sunlit hemisphere is instantly severed from UTC synchronization. When a network node drops its satellite connection, it enters a protocol called holdover. The system must immediately default to its internal hardware oscillator to maintain the local clock. This introduces a harsh mathematical reality. No physical oscillator is perfect. Without constant correction from the satellite feed, the local time immediately begins to drift away from true UTC. Primary national timing laboratories avoid severe drift by utilizing highly controlled cesium oscillators, which stray by only fractions of a nanosecond per day. Critical data centers might employ miniature atomic rubidium oscillators. These are stable enough to buy operators several days of holdover time, but they are expensive and rarely deployed outside of primary hubs. The vast majority of the world's commercial endpoints use basic Quartz oscillators to keep costs low. Survival during a prolonged satellite blackout reduces entirely to one equation: the duration of the atmospheric outage multiplied by the aggressive daily drift rate of commercial Quartz. This simulator maps the holdover trajectories of local hardware over a 72-hour satellite blackout. The vertical axis measures accumulated time error in microseconds, using a logarithmic scale to capture the vast variance in physical hardware. The baseline trajectory for a primary cesium oscillator remains exceptionally stable, flatlining across the entire 72 hours. A data center's rubidium oscillator shows a steady, mathematically manageable climb. Urgent, but the standard Quartz oscillator behaves completely differently. Without satellite correction, its time error rapidly accelerates off the baseline, drifting by up to 10,000 microseconds in a single day. Quartz hardware operates 99% of our network endpoints. That vertical red line is the exact trajectory of the global economy descending into dysynchronization. To understand when the systems actually break, we have to intersect that Quartz drift curve with the rigid engineering tolerances of our most vital sectors. The modern electrical grid uses phasor measurement units to measure alternating current across vast distances. These sensors require strict time synchronization to within roughly 1 single microsecond. If these units drift beyond that tolerance, grid operators lose all visibility of phase angles. They are forced to operate blind, drastically increasing the likelihood of cascading blackouts. Telecommunications operate under similarly brutal constraints. Cellular networks require a strict 1.5 microsecond limit to separate data packets. Watch the intersection. Within the first few hours of a blackout, the drifting Quartz breaches the absolute limit for both the grid and cellular data. At this exact threshold, cellular base stations are programmed to intentionally drop traffic and isolate themselves to prevent total data collision. The grid loses its safety monitors and global communications go dark, not from physical damage, but entirely due to localized hardware drift. Beyond physical utilities, the digital movement of global capital operates on an even tighter mathematical leash. Algorithmic high-frequency trading executes thousands of transactions in fractions of a second. Under international regulatory frameworks like MiFID II, financial ledgers legally require accuracy to within exactly 100 microseconds of true UTC. It is the only way to prove the definitive sequence of trades. When we plot that 100 microsecond regulatory threshold on the simulator, the timeline narrows further. As the Quartz oscillator continues its uncorrected trajectory, it inevitably slices through the legal limit for high-frequency trading. Breaching this limit immediately corrupts the absolute sequence of transactions. To prevent complete, irreversible ledger corruption, automated exchanges must enter a total, indefinite halt. Step back from the microsecond math, and the macro reality becomes clear. Atmospheric scintillation scrambles the satellite connection. Terrestrial networks are forced into a hardware holdover. They cannot sustain. The local clocks drift, and within hours, strict telecom, power, and ledger thresholds are violently breached. The sun does not have to physically destroy a single transformer or sever a single fiber optic cable to paralyze the global economy. It only has to break the sequence of time. Our digital civilization is built entirely on a synchronized, nanosecond heartbeat broadcast continuously from space. If the sky scrambles that signal, our terrestrial hardware cannot hold the rhythm. For more uncompromising analytical investigations into the physical architecture of our modern world, subscribe to the Insight Engine. True technological resilience requires engineers to understand not just how systems operate under perfect conditions, but the exact mathematics of how they fail.